All right. Good evening, everyone. Thank you, Krishna Kumar, for joining. I hope more people will join soon. This is 11th problem solving session of the course Aeroengine gas turbine cycles. And what I'm going to do today is we will go through what we studied in week 11 and we will solve one turbo shaft engine problem. Okay. That is the agenda for today's session. And if you have any doubts in between, please feel free to stop me. And People who are going to view this in YouTube, if you have any doubts, please come back on next week, same time on Sunday. And I think that is going to be our last session. This is 11th week, and the next week is going to be the final week, 12th week. So I would really appreciate if you could join the final week, because if you and after that you will be having exams. If you have any doubts, you can clear all your doubts in your next week. Okay. With that information, I will maybe start today's session. And what I'm going to do is, because of I have some connectivity issues from my side. So what I'm going to do is I'm going to turn off my video for now, and after I complete the problem, then maybe I will turn on. If you have any doubts, you can stop. So this is just for a smooth running of this session. By the way, you feel free to stop in between if you have any doubts. That shouldn't be a problem. All right. So let me go back to what we studied last week. Last week we studied about turbo prop engine, and this week we studied about turbo shaft, different class of gas turbine cycle, which is a turbo shaft engine. We also studied prop fan engines, right? And there are various other alternatives. Next week we will be. It's going to be even more interesting. We will be solving a component matching problem. So, for example, whatever we did till now is like designing the cycle for a design point. So during takeoff, we need a lot of thrust. So typically, cycles are designed for that takeoff point. Now, um, once you design that cycle, if you are planning to use the same engine, of course, you have to use the same engine at off design points, such as in the cruise condition. You will have to find its performance at the cruise condition, whether you are able to meet the what do you call the thrust you required for the cruise condition, whether the turbine work that you are generating is enough to drive the compressor, uh, and whether the area is enough for the mass flow rate to generate the thrust that you require during the cruise condition. All these things we will deal in the component matching problem. So next week you will learn more about component matching for a turbojet engine, and that's where we will stop the course. And we will, for next week's sessions, we will solve one problem in component matching. Although that is not solved in the what you call in the course, but it would be a good idea to give you an idea about how why the component matching is required, how it is done, and all these things. Anyway, so we will study more about component matching next week. But this week we have a turbo shaft engine and prop fan engine. So quickly we will go through what we studied in the turbo shaft engine. So compared to IC engine, it has a lot of advantage. First of all, the turbo shaft engine is nothing but you have to use the energy uh, to drive the shaft basically, and the shaft is connected to for example, if it is used in the helicopter, it is connected to the propeller. Also in any propeller based engines, you will directly connect the uh, free turbine to the propeller. And for the gas turbine land based power generation engines usually are turbo shaft engines, where you generate power in term and you know, deliver the power in the shaft, which is used to which you can use it to connect it to the generator to generate electricity or whatever you want. But the main goal here is to get as much as shaft power as possible. Till now, we were studying about how to get higher thrust, but the turbo shaft is about how much higher power, how much power you can extract from the turbo shaft engine. So it is all about that, and the cycle is same. Only thing is, in addition to turbine, instead of having a nozzle, you will have another free turbine, which is going to extract all the energy from the or most of the energy from the turbine exhaust after the HP turbine or the LP turbine, which is going to run the compressor. So after you run the compressor, whatever the remaining work done left or work energy left in the it will be extracted using a free turbine, and that shaft power is connected to your power devices. So that is the idea of turbo shaft engine, and you could also do this with using IC engine, but the turbo shaft engine provides further advantages compared to IC engines, such as like high power to weight ratio. It is more reliable, compact in design, it constantly gives you the power output. Uh, it's versatile, lower noise levels. Fuel efficiency is very high compared to IC engines. It can also be run in high altitude. Performance is good, quick startup, low vibrations, greater power control. It also requires reduced maintenance compared to IC engines. There are also challenges since you have shaft, your complexity increases, cost increases, maintenance you have to do. It is it is it is easily maintained compared to IC engine, but in general and turbo gas turbine engines, the maintenance is higher for turbo shaft engines. So the weight is greater than the aero engines. For example, if the thrust compared to thrust producing engines, the turbo shaft engines weight is higher for the same class if you compare. So specific fuel consumption is higher, thermal management you have to do, noise levels are there. So all these are challenges when compared with in general in the gas turbines cycles, but it is offering better advantages than IC engines. So there are various types of turbo shaft engines. I'm just showing few here. For example, we have single spool turbo shaft engine. We have a turbo shaft with a recuperator. We already studied the intercooler and regenerator cycle, so it shouldn't be a surprise for you. So this is recuperator. Now you have like a two spool turbo shaft engine where one spool runs the compressor and the booster. The other spool is the free turbine. The other one is like you have two different compressors and two different turbines, and similarly double booster on HP spool, double booster on LP spool. Uh, you have two spool gas generator and separate power turbine. So all these are like a two spool turbo shaft variants. Okay. So now you are very good at how to identify this. I'm not going to get into details. So, but let's look into the cycle performance analysis. So here again, you have like most of the components are same. Only that you do not have a nozzle component, and typically turbo shaft is defined so that all the power is expanded, which means you are going to so after the air goes through the compressor and combustion chamber and the turbine, at the exit your air will be of very close to the pressure and temperature, or basically the pressure of the air will be of very close to the ambient. So typically we expand it till the ambient. Okay. And the expansion here is not nozzle expansion. Here it's the turbine expansion where you are extracting all the energy of the air or the gases in the power turbine or free turbine. Okay, which is connected to the load. So let me quickly check whether the recording is going. Yes. Okay. So the components are same. So first you have an intake, and it also has a diffuser efficiency. and you have compressor where you will have a compressor isentropic efficiency. You can find the pressure ratio of the compressor is given, and after air gets pressurized in the compressor, it is going to go through the combustion chamber where you will add fuel and increase the temperature to TT flow, T0 flow. So turbine entry temperature, and the gases which comes out of the turbine comes out of the combustion chamber, gets into the high pressure turbine or HP turbine, and here the work done by the HP turbine is equated to the work done by the compressor. You can see that there's only one compressor, and you have like two turbine. One is HP turbine, another is free turbine. So the HP turbine runs the compressor, and equating the work will give you the pressure and temperature. Um, and for free turbine, you can assume a maximum power recovery. Maximum power is you can expand it from 5 to 6, you can expand it to the atmosphere, P infinity. Okay. And yeah, so for this expansion, again, it's a turbine. We already know P6, so based on that, you can find the temperature. So P6 is nothing but P infinity. You substitute that, and you can find the temperature. So this is the only change that you have compared to other cycles. In power turbine, you assume it's a maximum power recovery, and the pressure at the exit of the pressure of the gases at the exit of the turbine is going to be same as the ambient pressure. Typically, that's the case. It's almost equivalent to ambient pressure, so or slightly higher. But so here it doesn't matter. So from the efficiency of the turbine definition, you can rearrange it to find the temperature at the exhaust. Okay, and once you find the temperature at the exhaust, you can find the performance parameter. Here there is no thrust. Here you have only power. Power for the free turbine is nothing but the total. So for this you need temperature, as I said. So once you find the temperature, you know what is the total energy extracted from T05 to T0 uh, from T05 to T06. So from there you can find total power uh, at the free turbine rotor, and you will connect it to a load and through a shaft, and therefore the shaft has a mechanical efficiency. So the total power delivered to the load is going to be eta m times power at the free turbine. Okay, and the thermal efficiency is going to be expansion work minus compression work divided by m dot f into qr, or simply the shaft power divided by m dot f into qr. This is the thermal efficiency. And finally, the thrust specific fuel consumption here becomes brake specific fuel consumption, BSFC. Okay, so the BSFC is nothing but the amount of m dot fuel required per unit shaft power. Okay, so these are the performance parameters. So it's fairly simple compared to other turbo engines. So this is about turbo shaft engines, and there's also one more class that we studied is the turbo prop fan engines, where it's similar to turbo shaft till high pressure turbine. The remaining gases are expanded partially among the free power turbine and some of the exhaust gas. Okay, so typically you have another turbine which runs this big fan, and which is nothing but the aft fan. The fan is not at the front; it is at the back. That is how it is different compared to turboprop and the also turbo fan engines. So that's why this is called prop fan engines. And the remaining gases are expanded through the nozzle. Okay, so this is typically used for thrust applications. Okay, and I guess one of the problem that is given for your week 11 assignments is prop fan engines. So here the aft fan operates against the free stream and discharges to the atmosphere. They usually have a very high bypass ratio, uh, and due to prominent free stream capturing ability, which means the fan is very big, so therefore they have very high bypass ratio, and they are usually for 2 and 3 spool type configurations. So uh, again, the calculations here are simple till the HP turbine, and for the LP turbine, also for the LP turbine, which is running the LP compressor. So until then it's fine. And the remaining is the ducted fan. So across ducted fan, you may need to find out what is the total temperature change. This is from the fan calculations. You already know. So total pressure at the fan exit is given. So unducted fans pressure ratio will be given, and based on that, and also the efficiency of the unducted fan is given. Based on that, you can find the temperature uh, from uh, from the inlet of the unducted fan to the exit of the unducted fan. You can find out. Inlet is going to be simply the free stream pressure and temperature. Exit is going to be based on the pressure ratio across the unducted fan. Okay. And then you have a free turbine and nozzle, where you will have uh, the the nozzle. Some power is going to be extracted in the free turbine, and the remaining power is going to be extracted in the nozzle. So the amount of power extracted at the free turbine is given by this pressure split factor, which we studied in the turboprop engine. So we have to follow the same procedure. So here you have the power split factor that is going to help you find the work developed by the free turbine, and the remaining delta H is going to be used for nozzle. Okay, so alpha times delta H, and 1 minus alpha times delta H is expanded in the nozzle. And based on whether the nozzle is choked or unchoked, you will use different relations. So finally, the performance parameters is going to be the bypass ratio. You may need to find out, because we do not have the bypass ratio here. So the bypass ratio we can find based on the amount of work the unducted fan has been used, and the unducted fan's work is actually provided by the free turbine. So when you equate them, you will end up having so the unducted fan's work is nothing but m dot, that is crossing through the unducted fan, to CPC T011 minus T010. In this, the only unknown is m dot UDF, that is not given. And on the other side, the amount of power that is extracted in the free turbine is m dot C into 1 plus F into CPC times T07 minus T08. So from here, m dot UDF by m dot C is nothing but beta. You already know the temperature, so from there you can find the bypass ratio. So this bypass ratio would be very high. Okay, and the total thrust is going to be thrust through the unducted fan plus thrust through the nozzle. So unducted fan thrust, we have beta m dot A into V, velocity at the exit of the unducted fan, minus V. So VE, this is already we found from here, the exit velocity through the unducted fan. It is nothing but the total energy change, right? So this is equal to square root of 2 CPC T naught infinity minus T12. So how do you get this relation? So this is nothing but VE UDF square by 2 is equal to CPC times delta T. Okay, so the total energy change that the air goes through across the fan is going to be equal to adding a the additional velocity, or the total energy change is going in the form of kinetic energy in the fan. Okay, so the amount of energy change is going in the form of kinetic energy. So that is how you find the exit velocity through the unducted fan, and that exit velocity you already know. So that is used to find the total thrust through the unducted fan plus the nozzle thrust. Okay, so this is the total thrust, and you also have oh yeah, so V infinity minus VE minus V infinity is the unducted fan's thrust, and I no need to explain you how the thrust is coming for the nozzle. So that is the total thrust. Finally, the thrust ratio is also one of the parameter people look at, which is nothing but the thrust through unducted fan divided by thrust through the nozzle. And since this is also kind of like a prop engine, we can also check how the power characteristics are. So the equivalent power is going to be power through unducted fan and the power through nozzle. So which is simple, you take the thrust multiplied by the velocity of the aircraft, which is flying at V. The same goes with the nozzle. And finally, the propulsive efficiency is nothing but the total power or the equivalent power. This is nothing but equivalent power. Or you can also write it in terms of total thrust times V infinity. As usual, we write it for any turbo jet or turbofan engines, divided by the total power plus the amount of kinetic energy wasted in the core stream and also in the uh, unducted fan stream. Okay, so this is your propulsive efficiency. Similarly, you have thermal efficiency and also you have overall efficiency. Finally, you also have TSFC, which is m dot f into TUDF and TN. We also know equivalent shaft specific fuel consumption. So equivalent specific fuel consumption, which is based on the equivalent shaft load. So that is we studied for a turbo prop engine. So you can find the both specific fuel consumption. So these are the important performance parameter for the prop fan engine. Okay. All right. I hope it is clear both the turbo shaft and turbo prop fan engines. So what I'm going to do is I'm going to solve one problem in turbo shaft engine. Okay. All right. So this is your single spool turbo shaft engine, which we are going to solve today. And uh, the TS diagram would look something like this. You have initially you have P infinity, and from infinity to 2 you have the inlet diffuser, so which across which the air gets compressed from P infinity to P naught 2. Or in yeah, so you could it's due to the ram effect. And from P naught 2 to 2 to 3 you have compressor. And from 3 to 4 you have a combustion chamber in which you are adding the fuel. And uh, but there is also a slight pressure loss, so that's why P03 is not equal to P04. And from 4 to 5 you have HP turbine, and the amount of work you extracted from 4 to 5 is used to drive the compressor from 2 to 3. Okay. And after this, from 5 to 6 you have uh, free turbine, which whose power you are extracting it and giving it as a load to the power driving machine, driven machine. So this is the load. Um, this is how a typical TS diagram would look. This is for a single spool turbo shaft engine. But I think now you guys are very well experienced and also experts in doing a TS diagram for any number of spool configurations. So today I'm going to solve one problem. I think this problem is already being solved in the class, but with a different compressor ratio. So here uh, I have like a heavy duty turbo shaft engine, which is operating at a flying condition of Mach 2.21, and the ambient pressure and temperature is given. The pressure ratio here I'm going to take it as 10.5. Okay. So in the lectures, I think you might have noticed the pressure ratio we used was 9.5. I just want to change some parameter and see the effect of pressure ratio for turbo shaft engine. Uh, but by now you should have already guessed what should be the effect of pressure ratio uh, for any gas turbine cycles. We have already studied this multiple times for turbojet, turbofan engines, and also I think turboprop engines. Um, so uh, I guess you should be in the position to guess what are the things that would affect if you change the compressor pressure ratio. Okay. But anyway, we will solve today and we will understand it better. So, and the turbine inlet temperature is 1320 Kelvin. Total pressure loss in the combustion chamber is 2%. The fuel heating value is 44,000 kilojoules per kg. And the core engine mass flow rate is 12 kilograms per second. Okay. And these are the given parameters, and there is also efficiencies associated with each components. For example, you have a diffuser efficiency of 92%, HPT turbine efficiency of 88%, burner efficiency of 98%. These are typical for a turbo shaft engine. Okay, so you could see that The free turbine and HPT turbine efficiencies are slightly lower. Um, Typically, the turbines efficiencies you know in a thrust generating gas turbine cycles, for example, turbojet or turbofan, the efficiencies are higher, but for turbo shafts, it's slightly lower. Okay, the compressor efficiency is 84%, mechanical efficiency is 99%. That's fine. The gamma C and gamma H, CPC and CPH is also given. Okay. So for flight condition with the compressor ratio of 9.5, these are the parameters that we got. You can go over the lectures to check these numbers. So the power uh, from the free turbine is 3896 kilowatt. And the are 3.89 megawatts, and the power that is delivered to the load because of mechanical efficiency, 1% of 3896 is lost, so you have only 3857 kilowatt that is delivered to the load. Okay, and the brake specific fuel consumption is somewhere around 0.077 grams per kilowatt second, and the thermal efficiency was 29.52 percentage. So now if we increase this compressor ratio to 10.5, what would be its effect is what we have to calculate. So the first, the hint is going to be similar. By now, you are experts. So first we will solve inlet, find the pressure and temperature after the inlet, and then you have compressor. Across compressor, there is a pressure ratio of 10.5. So the pressure from is going to jump from P02 to P03, and in this process, temperature also rises. And then it goes through the combustor where the fuel is added to reach the T04, which is 1320 Kelvin, and using that energy balance you will find F, and we will also find P and T. T is already known. We will also find pressure at the exit of the combustor because there is a 2% loss of pressure in the combustor, and the gases from the combustor enters the HP turbine, which drives the HP turbine, and uh, the shaft is then connected from the HP turbine to the compressor. The total power extracted at the HP turbine is used to drive the compressor. So that would give you P05 and T05, and then you have LP turbine, or in this case, the free turbine, whose entire power is given to the load. Okay. So this is the hint. So we will solve how uh, you know the change in compressor pressure ratio is affecting the performance parameters. So here what I'm going to do is I'm going to present the values that we got in the lectures too in this in the right hand side of the slide, so that we can directly compare. So intake is not going to change much because you have only changed the compressor pressure ratio. So intake is going to be almost similar. So the mark is 0.21. Pressure and temperature of the ambient is 51 kilopascal and 252 Kelvin. So the pressure you can find it to be around 52.46 kilopascal, and the temperature is going to be around 254.2 Kelvin. Here I didn't explicitly substitute the values because it's going to be same as this one. Okay, so I'm not changing anything in the inlet. So in intake is going to remain same between the two problems. The next is going to be the compressor. This is where changes are going to happen. Across the compressor, your pressure ratio is 10.5, so the pressure is going to be higher than what we got in the lecture. So here the P03 is 550.83 kilopascal. At any point, what you can do is for the people who are going to watch this in YouTube, you can stop the video and you can solve it with me. Okay. Um, Anyway, so the pressure at the exit of the compressor is 550.83 kilopascal, and from the isentropic efficiency definition, you can find the temperature at the exit of the compressor. So if you plug those values in, here your value is 10.5, however here it is 9.5. So you expect temperature also to rise from 527.34. If the pressure ratio increases, the temperature is going to be around 544.05 Kelvin. So there's around like roughly 20 Kelvin, roughly 17 Kelvin difference. Um, so with this high temperature, it enters the combustor, which means uh, we are going to add only less fuel to reach 1320 Kelvin because the inlet temperature itself is high. Okay. So therefore, so initially we will calculate the pressure loss across the combustor. The pressure of the air entering the combustor is 550.83 kilopascal, and 2% pressure is lost. Therefore, you would reach roughly 539.81 kilopascal. And for the combustor, you do energy balance. Energy balance is nothing but the energy of air entering, which is m dot c CPC T03 is the total enthalpy of air entering, and the total enthalpy that is added as in terms of fuel is nothing but m dot f into calorific value of the fuel into burner efficiency, which is eta B. This is equal to the total energy exiting the combustor, which is m dot c plus m dot f into CPH into T04. Okay. So here the only unknown here is m dot f. So you can rearrange it, write it in terms of m dot f by m dot c, which is fuel to air ratio, which we will be writing it in this form. Okay. So we already know T03, T04, and CPH and CPC. These are all given values. So you substitute them, and as expected, you would end up having lower fuel to air ratio. This is because your inlet temperature is higher, so you need to add only less fuel to reach the same temperature. In both the problems, you are reaching the same T04 temperature, which is 1320 Kelvin. So you will be adding less fuel to reach the same temperature. So this is no surprise. So the fuel to air ratio is 0.02347. Okay. Now the next is you have HP turbine. Now the HP turbine has to drive the compressor. So which means uh, what would happen with the pressure and temperature at the exit of the HP turbine, right? So that is the question here. So you can do the energy balance to find out work done by the compressor, work extracted at the HP turbine is equal to work done by the compressor. But before doing that, you can probably do some guesses. So compared to this value T05, we got for a compressor pressure ratio of 9.5, we got temperature at the exit of the HP turbine to be 1088 Kelvin. Now you can see that we will have to provide more work to the HP compressor. Uh, the reason is your compressor pressure ratio has increased from 9.5 to 10.5. So therefore, a lot of energy needs to be extracted from the HP turbine. And if the energy extraction increases, you expect the temperature at the exit of the HP turbine to be slightly lower. What is also true is the amount of fuel that we added is also less. Okay, so the entire turbine is operating at a lower mass flow rate compared to the lecture problem, and it has to deliver higher work. Okay, so in that way, we should expect T05 to be lower than 1088 Kelvin. So let's do the calculation. So we have energy balance work done by the HP compressor is equal to work done by HP turbine. Here the HP turbine has m dot core into 1 plus F, CPH T04 minus T05, which is equal to m dot core into CPC T03 minus T02. Okay, and if you rearrange them, you will end up having the temperature around 1073.36 Kelvin, so which is lesser than 1088 Kelvin, around roughly, I guess, 15 Kelvin lower. Okay. So now we should also need to find out the pressure. For pressure, we will use the compressor, sorry, the turbine efficiency, which is going to be based on the pressure ratio. So P05 minus P04 is equal to 1 minus T04 minus T05 divided by the efficiency of the HP turbine times T04. You should also note the turbine efficiencies are lower here. So typically we do not have 88% turbine efficiency in turbojet or turbofan engines, but here the efficiencies are lower. Anyway, so if you do this calculation, you end up having the pressure ratio to be again lower, and it is as expected. We will expand it more, right? So the pressure also has to be lower than whatever we got in the lectures. Okay, so this is what we got, which is roughly 206.29 kilopascals. Uh, yeah. Um so now there is a contradiction. You have like we said that we need to extract more energy out of the HP turbine because because the compressor requires higher power. Um, so you will expect the pressure to be lower than 198.98 kilopascal. But uh, what is true is the entire cycle is operating now at a higher pressure. So because the HP compressor has reached very high pressure because of 10.5 pressure ratio. Therefore, the extraction here is also happening at higher pressure. Therefore, you do not have uh, lower pressure. You're not seeing pressures lower than 198.98 kilopascals. You are seeing slightly higher pressure, which is around 206.29 kilopascal. Okay, so which is like 8 kilopascal or 7 kilopascals high. Okay, this is because the pressure ratio, the compressor has raised the pressure. The highest pressure that you will see in this entire cycle is going to be at 3, right? Which is right after the HP compressor, or in this case, compressor. Here, since the compressor pressure ratio is higher, the highest pressure that you are seeing here is this much. Okay, uh, and therefore your turbine expansion is also happening beginning at a higher pressure, and therefore that's why you see higher pressures at the exit of the HP turbine. Anyway, so the P05 is 206.29 kilopascal and T05 is 1073.36 Kelvin. Now the then this gas is going to go through the LP turbine, and the LP turbine is going to extract as much as energy as possible. It cannot continuously extract energy because the air also has to leave the engine, and it cannot leave the engine at a pressures lower than the ambient condition. So typically the expansion should happen for a maximum power extraction. The expansion has to happen only up to ambient condition. So from P05, which is around 206.29 kilopascal, it can expand up to the P ambient, which was around 41 kilopascal or something that we saw. Okay, so which was 51 kilopascal. So that's just the maximum power, maximum pressure. That's the minimum pressure it can reach. It cannot go below this. Okay. So we will assume maximum power expansion for this one also. So free turbine expansion to the ambient condition, and therefore P06 is already known, which is the ambient condition, and therefore you can rearrange this equation to write it in terms of temperature. We need to find temperature at the exit, temperature of the uh, gases leaving the free turbine, because the total temperature change multiplied by Cp is the enthalpy change, which is the amount of work that you extracted from the free turbine. Okay, so to determine the amount of work from the free turbine, we need to find out temperature at the exit of the free turbine. So which is what we are finding it here. We also included the isentropic efficiency in here, and this corresponds to a temperature of around 796.6 Kelvin. So since the temperature is already lower, T05, the here also temperature is expected to be lower, so which is around 796.6 Kelvin. This is the temperature of gases that is leaving the LP turbine. Okay, so then now you can find the work. So power delivered to the free turbine rotor, which is nothing but m dot c into 1 plus f into cph. So the expansion is happening from T05 to T6, which is what we are writing, T05 minus T6. So this is equal to roughly 3922.52 kilowatt. So the power that we got when the compressor ratio to be compressor pressure ratio of 9.5 was 3896 kilowatt, and since you increase the compressor pressure ratio, your the power delivered has uh, increased to 3922 kilowatt, okay, or 3.92 megawatts. So this is the total power delivered to the free turbine rotor. but since it is connected to a load through a shaft, the mechanical efficiency comes in. So the power delivered to the load is 99% of this, which is roughly 3883.3 kilowatt. Okay, which is also higher, which is I think 30 kilowatts are so higher than the roughly 30 kilowatts higher than what we got for the compressor pressure ratio of 9.5. Okay, now let's calculate the thermal efficiency. Thermal efficiency is going to be shaft power divided by m dot f into qr. Uh, Here the fuel to air ratio has reduced and the shaft power has increased, and therefore you should have higher thermal efficiency. That is what we got, which is around 31.65 percentage. So by increasing the compressor pressure ratio, you have increased your thermal efficiency. So now one question is, does that mean if I continue to increase pressure ratio, will my thermal efficiency continue to increase? So that is a question that you should all think about. We already know the answer. You should. This is just to recap what you studied till now. So if you keep increasing the pressure ratio, what happens is your inlet temperature to the combustor also keeps increasing. Therefore, you end up adding lower fuel, more and more low fuel, and if you keep adding lower fuel, the power at the output also keeps reducing. Okay, so there is a peak, there is an optimal compressor pressure ratio that is, if you do this calculation again and again for different pressure ratios, you can, you and if you plot these performance parameters, you will find an optimal peak or an optimal compressor pressure ratio for which you will get a maximum thermal efficiency. So think about it, about the thermal efficiency. It is not linearly increasing. You cannot keep increasing the compressor pressure ratio. For this case, when we increase the compressor pressure ratio, it is beneficial for us because our shaft power has increased with a lower fuel consumption. So therefore, thermal efficiency also increased from 29.5 to 31.6 percentage. Okay, and the brake specific fuel consumption, we expect it to increase because power has increased, m dot f has reduced, so we expect bsfc to reduce. So the amount of fuel that you need is only around 0.078 grams to generate 1 kilowatt uh, of power. Okay, 0.078 grams per second to generate 1 kilowatt of power. So your brake specific fuel consumption has also came down, so which is beneficial in this case. So in this case, when we increase the compressor push ratio, it's beneficial. Okay, so it's not always true, so please remember that. And so this is the final side by side comparison of how the performance parameters are increased from, you know when you increase the pressure ratio from 9.5 to 10.5. So your power in the free turbine has increased around 30 kilowatts. The same with the power delivered to the load, and the BSFC has reduced and thermal efficiency has increased. Okay, all right. So this is what I wanted to share with you today. If you have any questions, please feel free to stay back and ask me. And I will be anyway available here in this platform till 5 o'clock. And yeah, so I hope this will be useful for you for solving the week 11 assignments. And we will meet next week then. We will solve one problem on component matching. Although I don't think component matching problems are there for your week 12 assignments, but I think it will be useful for you in in general. Okay. All right. Thanks for joining. Thanks for the people who are going to watch this in YouTube. And if you have any doubts, please feel free to reach out to me. Uh, I would be happy to help. And if not, we will meet next week. So next week is going to be our final problem solving session of this course. All right. Thank you very much.